General equilibrium crash course. So here we go. So first of all, we have to be able to look at our concentration versus time graphs from kinetics and tell when equilibrium is established and what K represents. So if I look at my concentration versus time graph, my reactants decrease their concentration over time and my products increase their concentration over time. The time in which equilibrium is established is when both of the reactants and products flatline. So that is the time in which equilibrium is established. There's another graph right here, and that is showing reactants decreasing over time, products increasing over time, and when those flatline, equilibrium is established. K is known as your equilibrium constant, and it is temperature dependent. Temperature dependent. So the only time when K changes is when your temperature changes. I have two different Ks, Kc and Kp. We know that there's others that we have going on, but those are the only ones I'm going to talk about in this video. So Kc is dealing with molarity. So when we write our products over reactants, then we write those in brackets. We raise our products to the coefficients. It's products concentrations over reactants concentrations, and they are each to the power of their coefficient. If I'm writing a Kp expression, you cannot put those in brackets because brackets denote molarity. So you have to put parentheses around it. Pressure of my products raised to the coefficient over parentheses pressure of my reactants raised to the coefficient. So that's the difference between Kc and Kp. Kp is dealing with atmosphere, Kc is dealing with molarity. If I solve for a K value and K is greater than 1, that means that the products are favored. Delta G is negative because it's thermodynamically favorable. If K is less than 1, that means that the reactants are favored. Delta G is positive, indicating that the reaction is thermodynamically unfavorable. Another thing you have to remember while writing these expressions is pure solids and pure liquids are never in your expression. So when you write your expression for this, you don't plug in any numbers except for the coefficients. You plug in what the products and reactants are, and you never include solids and liquids because they are so high in concentration that they are not going to change drastically. Now let's talk about manipulating K. This is very similar to Hess's law of summation, but you have to manipulate K differently than you do delta H. So if you reverse a reaction, what you do is you take 1 over K. If you multiply a reaction by some number, then you take K raised to that power. And if you add equations, rather than adding K's, you multiply your K values. So this is used if you have different reactions and K values. Say a third reaction and K. And you want to find the overall K for all of these reactions added together to make a goal equation. So if I double this reaction at the top, I have to square that K value. If I want to flip this last reaction, then I'm going to take 1 over K for that value. And then if I add these reactions to make this goal equation, instead of adding all of your K values, you have to multiply those K values to one another. The relationship between Kp and Kc, they're not interchangeable. So Kp deals with pressure, so when you do your Rice chart, those are going to be atmospheres that you plug in there. Kc deals with molarity, and so your Rice chart is going to have molarity in there. This is your conversion equation. I call it the politically correct to change the nation equation. The reason why is KP, politically, KC, cur, and then RT for the correct. And then to change the nation, a lot of students forget this part. Delta N stands for the moles of gas in my product side minus the moles of gas in my reactant side. So if I had 2 moles of gas plus a solid yields 3 moles of gas on my reactant side or my product side, it's products gas minus reactants gas. So delta N would be 3 minus 2. It's okay to have negative delta N quantities. So if I had, for instance, only 1 mole of gas on this side and 2 moles of gas on that side, products would be 1 minus 2. So it's okay to have -1, a negative quantity for my delta N. So that's how we convert Kp to Kc. They are not interchangeable. Now the next thing is Q versus K. K is for initial values. Whenever you see the word initial, that is your keyword to be able to use Q. So this is for the I part in your rice chart when you're doing your rice tables for equilibrium. Remember, K is only for equilibrium values, and this is the E line in your rice chart. Sometimes you don't know which way the reaction is going to go, so you don't know where to take your minus x's and plus x's, so you have to find Q to figure out what's going on there. So you use your initial values to find Q. If Q is less than K, then that means that the reaction has to proceed to the right in order for equilibrium to be established. Q less than K means that equilibrium hasn't been established yet. So what we say is that the products are favored. The reaction is going to proceed to the right, and on top of that, if we look at delta G in relation, anytime my products are favored, delta G is negative. If I have that Q is greater than K, then what's going to happen is my reaction is going to proceed to the left. This means that my reactants are favored. And if my reactants are favored in relationship to delta G will be positive. If I decided to have N2 plus H2 yield NH3, and that balanced reaction is a 2 there and a 3 there, and I add N2, what's going to happen with Le Chatelier is that the reaction is going to shift to favor the products in order to reestablish that equilibrium. This is an example of, instead of N2, H2 being added, this graph right here. So if H2 is, they're at equilibrium, so they're all flatlined, right? And then you decide to add your H2, well then it's going to increase, but then try to reestablish equilibrium. So these things right here, the N2 and the H2, are going to decrease in value, and the NH3 is going to increase in value in order to establish equilibrium again. So they might throw one of those graphs in a multiple choice question, so you got to know how to be able to do that. If you're working with volume or pressure, if pressure increases, you always move to the least amount of moles. Now, the only thing that can be pressurized is gas. So it's the least amount of moles of gas. So here, these are all in the gas state. You have 4 moles of gas on this side. On this side, you have 2 moles of gas. So if my pressure increases, that reaction is going to shift towards 2 moles. If the pressure decreases, it's the opposite. For a change in temperature, it depends if the reaction is endo or exothermic. So H2 goes to 2NH3. Let me put a 3 there. This reaction, let's say, is exothermic, so heat is a product. So that means if I end up increasing temperature, I increase right there where the heat is, and so the reaction is going to shift towards the reactant side. Remember that temperature is the only thing that can change your K value, because K is temperature dependent. So if the reaction is shifting towards the reactant side, that means there's more reactants being made now, so K will decrease. If temperature causes a change to where your reaction shifts to the product side, K will increase because now I'm making more products.